Hello students, this is lecture 16 of MTH 201. In the last lecture we discussed extrema of a function of two variables, critical points, and we also discussed first derivative test and second derivative test to test the nature of the extrema. There was a typo in lecture 15. In the hypothesis of second derivative test, I had mentioned C1 function, but in the bracket I had written functions which have continuous second order partial derivatives. So actually you need continuity of second order partial derivatives for the second derivative test, and therefore the function is a C2 function. Okay. So this is something that was incorrectly written in lecture 50. Okay. So today we are going to look at a test, a very important test or a very important method to compute absolute maxima, absolute minima of a function. Okay. So let us proceed. I will first talk about this example, which is a very simply posed example, and you can actually find a solution to um, this problem by something else that we know. Okay. So, but anyway, let us see how we can solve it. So find the point on this plane 2x minus y plus 2z equal to 20 that is closest to the origin. Okay. So from geometry we know that the point that is closest to the origin on this plane is actually that it'll form a perpendicular, right? It will be normal to the plane, right? So that way you can actually compute what that point is. You can also compute what the distance should be. And we have looked in lecture 4. We have looked at in lecture 4 the distance between a point and a plane. So you can compute the distance directly. You can also compute the point. So let us do it differently. So let xyz be a point on the plane. Then from this equation we know that z should be equal to 10 minus x plus y by 2. So you can bring these terms on the other side, and this is what you get. Now what is the distance between origin and this point? It's given by square root of x square plus y square plus z square, right? This is the distance between 0, 0, 0 and this point x, y, z. But from the previous step, z is of this form, right? So you can replace z by in terms of x and y. So what you have on the right is solely in terms of x and y. So now using this expression, you consider this function fxy, which is basically square of this term. Okay, it's the square of the distance between origin and this point which is on the plane. What do we need to do? We need to find a point which is closest to the origin, which means that we want to minimize this distance, right? We want to make it as small as possible. So we need to find a point which is an absolute minima of f, right? Okay. It is smaller than everything else. So taking a square will not make a difference, because if this square function is minimized, then obviously this will be minimized. Okay, so let us first find critical points of f. How do you do that? You compute the first partials, set them equal to 0, and this is what you get. X equal to 40 by 9 and y is minus 20 by 9. And from there you can compute z, because z has this expression, this point lies on the plane. So you have this point and you're getting just one critical point, right, in this case. Now the question is what happens at other points, right? So now there can't be any more critical points, right? So local extrema are done, right? There are no other local extrema. But this plane is an infinite plane, right? X, Y, Z can take infinite values. So if X and Y approach either plus infinity or minus infinity, what happens to this function? This function also shoots to infinity, right? Because if X goes to, let's say, plus infinity or minus infinity, then this term goes to infinity. Everything else is non-negative. So everything shoots up to infinity, right? So that means whatever distance we will get from this point will be smaller than what happens is as you go towards the end of the plane, right? Which is when X and Y approach plus minus infinity. Therefore, by simple inspection of the function, you know that the minimum value is attained at this critical point only, right? Now, there is another way to check whether it's actually a minimum, at least a local minimum, is you can also use second derivative test. You can also compute the Hessian matrix and use second derivative test to actually check that this will be a local minimum. Okay. But there is no need in this case because you know that as you go away from this point, your distance is becoming larger and larger. So therefore, the closest point to the on the plane to the origin is given by this point. And what is the distance? Distance between origin and this point is square root of x square plus y square plus z square, which gives you 20 by 3. Now by direct calculation from lecture 4, you can also compute distance, which also comes out of course to be 20 by 3 by using the normal to the plane and so on, right? So this is something that we have seen in lecture 4. Okay, so I'm going to use this example as an inspiration and let us now uh, define a method which is called Lagrange multiplier method to compute absolute maxima on a domain. Okay, so let us see what we mean by this. So there are various versions of Lagrange multiplier method. We are first going to talk about two variables and one constraint. So what do we mean by that? So this is our question. Find the extreme values of fxy subject to the constraint of the form gxy equal to k. What does it mean? In other words, find the extreme values of this function of two variables when the points lie on the level curve gxy equal to k, which is R2, right? So I am restricting my domain to this level curve, and on this level curve I am checking what are the extreme values of this function. So this is the question. So let us see how to so this slide is basically going to be why Lagrange multiplier method works, which will be studied on the next slide. So I'm just giving you the background. Okay. So let x naught y naught be an extrema of fxy where the points xy are restricted to the level curve this. So suppose this is the extrema. This is an extrema. Now assume this is an important assumption that we want on the level curve at this point. Okay. So gradient of g at x naught y naught is non-zero. Okay. Now geometrically, what is gradient of g at this point? It's nothing but a vector which is orthogonal to the tangent curve, the tangent line to this level curve at the point x naught y naught, right? So this is that vector. Okay. So now since g x naught y naught is k, gradient x naught y naught is orthogonal to the tangent line to the curve this at this given point. This is something that we have seen when we talked about gradient of a function of two variables at a point to the level curve. Okay. Now parameterize this level curve as Ct where the value at t equal to 0 is this point. Okay, so you imagine you are on this curve Ct, right, which is nothing but gxy equal to k, and at t equal to 0 you are at the point x naught y naught. Now you define this function ht, which is f of Ct. Now why are we doing this? Because we only want to restrict to the level curve, right? Now on the level curve, you want to find extreme values. Now what is the level curve now? We have parameterized it at Ct. So as t changes, this Ct moves along this curve, and therefore when you compute this f of Ct, you are looking at values of f on the level curve, right? So now it's a one variable function because I have parameterized my curve. Okay. Now f has an extrema at x naught y naught. That's where we started off with. Therefore, this h has to have an extrema at t equal to 0. Right? Because if f has an extrema at this point x naught y naught, and x naught y naught is nothing but c naught, therefore at t equal to 0 h has an extrema. But h is a function of one variable, and we know that if you have a one variable differentiable function and it has an extrema at a point, then the derivative is 0 at that point. Right? Now this derivative is 0, but by chain rule you can compute h prime t as gradient of f at Ct dot product with c prime t. So when you evaluate this thing, when you set t equal to 0 here, you get h prime 0, but h prime 0 from the previous step is 0. So you get 0 equal to h prime 0, that is equal to gradient f of c0, but c0 is x naught y naught, dot product with c prime 0, which means that the gradient of f at this point is orthogonal to c prime 0. So what is c prime 0? C prime 0 is nothing but the direction of the tangent line to the curve, right? Thus, this gradient of f at the point x naught y naught is orthogonal to c prime 0, and that is gradient is orthogonal to the tangent line to the level curve gxy equal to k at x naught y naught, because this c prime 0 is nothing but the direction of the tangent line, right? So now what do you have? You have c prime 0 and you have two vectors which are orthogonal to it. One is gradient of g at this point and other is gradient of f at this point. But you are in R2, right? In R2, if two vectors are both orthogonal to a given vector, then they have to be along the same line, right? Meaning that they must be linear multiples of each other. They can either point in the same direction or reverse direction. But that's the only option. Therefore, there exists a scalar such that gradient of f at this point should be equal to lambda times gradient of g at this point. Okay, and this is precisely what is Lagrange multiplier method. So pictorially, this is what we did. We had this curve which was gxy equal to k, and this was the point. You have gradient of g, which is perpendicular to c, this the tangent line to this curve at this point, and gradient f is also perpendicular. So they have to be linear multiples of each other. In this particular picture, they are pointing in opposite directions, but that's not necessary. They can also point in the same direction. Okay, the only thing is they are along the same line. So this is the method. What do? You compute gradient of f and gradient of g. You find values of x, y and lambda which satisfy two equations. One is gradient of f equal to lambda times gradient of g, and you also want to be on the curve, right? So gxy should be equal to k. That is, now expanding the first equation, which is gradient f is lambda gradient g. Now gradient f has two components, fx and fy, and gradient g also has two components, gx and gy. So when two vectors are equal, then they should be equal component wise. Therefore, fx should be lambda gx and fy should be lambda gy, and obviously the third one is important. So you will get three equations and you will solve for x, y and lambda from these three equations. Now find values of f at all the points obtained in the previous step. The largest value is the maximum value of f on the level curve and the smallest value is the minimum value of f on the level curve. Okay. So let me go back just a minute. So this was happening when your function was a function of two variables and there was one constraint. Now let us look at what happens when you have a function of three variables and one constraint. So the question is, find the extreme values of f, x, y, z, a function of three variables, subject to the constraint of the form g, x, y, z equal to k. Okay, we have added one more variable now. In other words, the question is, find the extreme values of f, x, y, z when the point x, y, z lie on the level surface. Now you don't no longer have a level curve, you have a level surface, which is given by this. So now what do? It's a very similar procedure, but now instead of a level curve g, x, y equal to k, you have a level surface. So you have to do something else. But very similar. So let x naught, y naught, z naught be an extrema of this function when the points are restricted to this level surface. And also we need this assumption that gradient of g at this point is not a zero vector, not the zero vector. Now since this point lies on the level surface, what do we know? This gradient vector is normal to the tangent plane to this surface at x naught, y naught, z. This is something that we have seen already. Now let Ct be a differentiable curve on the level surface passing through this point at t equal to 0. Okay. Now you consider you are doing the same thing. Now you are fixing a curve first on the level surface and you are looking at f restricted to that levels curve, and you define this function. So you do the same procedure since f has an extrema at this point, h has an extrema at t equal to 0. So by first derivative test, this should be 0, but by chain rule, h prime t is gradient of f ct dot product with c prime t. You set t equal to 0, this is what you get. So what you have is that gradient of f at x naught, y naught, z naught is orthogonal to c prime 0. What is c prime 0? It's the direction of the tangent line to this curve ct at the point t equal to 0. But there are more curves on this surface, right? So since ct is an arbitrary curve passing through this point, gradient will be normal to or orthogonal to all such c prime 0, all the directions, right? Therefore, gradient of f at this point is normal to the tangent plane to the level surface at this point. So again we are back to a similar situation. We have a fixed tangent plane to the level surface g, x, y, z equal to k at this point, and we have found two normals. One normal is of course the gradient of g at this point, and other normal is gradient of f at this point. So if you have a plane and you produce two normals, what should be relationship between those two normals? They should be linear multiples of each other. So since gradient of f and gradient of g at this point are normal to the tangent plane to the level surface at this point, they must be linear multiples of each other, and hence there is a scalar lambda such that gradient of f at this point is equal to lambda times gradient of g at this point. Okay. So this is the picture. You have this level surface gxyz equal to k. You have this tangent plane at this point, right? So normal to this you know is gradient of g at this point, but what we have got is that gradient of f is also normal at this point. Therefore, there should be linear multiples of each other. So what is the method? You compute gradient f and gradient g. Now it's a function of three variables. You find values x, y, z and lambda which satisfy these two equations. Gradient of f is equal to lambda gradient of g. They are linear multiples of each other, and g is equal to k. The point lies on the level surface. So, if you expand the definition of gradient f, gradient g and equate them component wise, we are solving four equations. Fx equal to lambda gx, fy equal to lambda gy, fz equal to lambda gz and g is equal to k. Now what do you do then after you have found these values? Find values of f at all the points obtained in the previous step. The largest value is the maximum value of f on the level surface, and the smallest value is the minimum value of f on the level surface g equal to k. So it's exactly the same procedure, it's just that now you have one extra equation, one extra variable. Okay. So let us look at this example where you have a function of three variables and you are given one constraint. So you have to maximize this function x, y, z subject to this constraint. Now this problem can be rephrased as a word problem as follows. Maximize the volume of a rectangular box with lid with surface area 20. So suppose you assume that the sides of this rectangular box are x, y, z, then its volume is x times y times z, right? So this is basically the volume function. And what is the surface area of this rectangular box if it has a lid? It's twice of xy plus twice of yz plus twice of zx. That will be equal to 20, right? So therefore, we are saying that we are fixing the surface area to be 20 and we want to maximize the volume of the rectangular box. So this problem could have been given to you, posed to you differently as well as this word problem. So we have to first set what g is. G in this case is xy plus yz plus zx, and this is the level curve, right? This is the constraint. So what is the method? You compute gradients of f and g, which are this. You solve for x, y, z and lambda, which satisfy these equations, which give you yz equal to lambda times y plus z, xz equal to lambda times x plus z, and xy equal to lambda times y plus z, and xy plus yz plus zx equal to 10. Now firstly, if lambda is 0, then yz, xz and xy are all 0, right? But can they all be 0? No, because if they are all 0, then 0 equal to 10 is the last equation, which is not possible. Therefore, lambda can't be 0. Hence, lambda is not 0. Now, if lambda is not 0, multiply with the first three equations by x by lambda, y by lambda and z by lambda respectively. So let us focus on the first equation. If I multiply both sides by x by lambda, I get x y z by lambda equal to x times y plus z, right? So what you get is xyz by lambda, right? Now second equation, if you multiply by y by lambda, on the left hand side you'll get xyz by lambda. Similarly, if you multiply the third equation by z by lambda, you get xyz by lambda. So they are all equal on the left hand side. So therefore the right hand sides are all equal. Okay. Now if all these are equal, this just means that all three terms should be equal. But if all these three terms are equal, putting it in the fourth equation, you get all three are equal and they should be equal to 10 by 3. Right? Therefore, all of them have to be non-zero. Right? Now, substituting this in the fourth equation, we get x and y and z equal to square root 10 by 3. Right? Because from the first equation, you will get y equal to z, and for the second pair you will get x equal to y. So in fact x and y and z are all equal, right? And they should be equal to square root 10 by 3. So you can do these steps. I have given almost entire proof here, but you can work this out on your own once. So the maximum value of f with the given constraint is this. So why are we getting only one? Why are we saying that this is the maximum value? Because from this step you are getting a unique point, right? You are getting a single point. So what was Lagrange multiplier method step 3? You at all the points that are obtained in step 2, the maximum will give you maximum, minimum will give you minimum. So since there is only one point, that has to be the maximum value, right? So how do you get this? This is nothing but substituting this point in the function, right? And in this case, what is Lagrange multiplier? What is lambda? Lambda can be obtained by solving any one of these equations, right? So lambda is yz divided by y plus z, which comes out to be this. So this, the lambda value is called Lagrange multiplier value. Okay. So note that in all these steps, we didn't really need the value of lambda, right? We eliminated lambda by first proving that lambda can't be 0. Okay. So you generally don't need the value of lambda in many problems, but whatever value you get where the maximum value, minimum value is achieved, that is called Lagrange multiplier value. Let us look at another example. Find absolute extrema of this function xyz on this ball. So it's actually a sphere, right? Uh, a, a sphere with inside, right? Everything included. Okay. So what do you do? First step is that you find extrema inside this ball. Okay, so this is my domain now. I'm not taking the boundary of the sphere. You find critical points. How do you find critical points of f? You set gradient to be 0. What is gradient here? Gradient is yz, comma, xz, comma, xy. So if gradient is 0, all of them are 0. So what does this mean? This means that all the points inside the ball having at least two coordinates 0 will satisfy this equation, right? And what is the value of f at all such points? It's 0 because it's product of these three numbers. And if at even 1 is 0, then you are done, right? So f takes 0 value at the only critical point in at all the critical points which are there inside the ball. Now what is extrema on the boundary, right? We have taken care of inside, but what about the boundary? Now let us use Lagrange multiply method. So you define the constraint to be xy square plus y square plus z square. So what is the constraint? G equal to 12. So you compute gradient f, gradient g. You solve for x, y, z and lambda from these equations. Gradient f is lambda gradient g and g equal to 12. From there you get these four equations, right? Now if I multiply the first three equations by x, y and z respectively, you get x, y, z, x, y, z, x, y, z on the left hand side, and the right hand side becomes 2 lambda x square, which should be equal to 2 lambda y square, which should be equal to 2 lambda z square, right? Now if lambda is 0, then yz should be xz should be xy, right? All should be 0. That is, two of the variables x, y, z are 0. Now if you substitute these in the fourth equation, which is g equal to 2 with g equal to, sorry, this should be g equal to 12. G equal to 12 meaning x square plus y square plus z square equal to 12. You get these 6 points, right? And at all these points, the value of the function is 0, right? Because two of the coordinates are 0. Now, if lambda is non-zero, then what happens? You can strike off these lambda from here and 2 as well, and you get x square equal to y square equal to z square. So if you substitute this in the fourth equation, which is gxyz equal to 12, you get, what do you get? You get x square is equal to 12 by 3, right? Which is 4. So x should be equal to plus minus 2 and y should be plus minus 2, z should be plus minus 2. So you actually get 8 solutions, right? All the possible combinations of pluses and minuses. Now at all these points, what is the value of the function? It's either 8 or minus 8. It will be 8 if even number of coordinates have negative sign, and it will be odd if, it will be negative 8 if odd number of coordinates are negative. Okay. Therefore, the maximum value of the function is 8 and it is attained at these 4 points, and minimum value is minus 8, which is attained at these other 4 points, right? And at all other points that we got, the value is 0, right? Which is bigger than minus 8 and smaller than 8. So there are a lot of calculations in this exercise, but it's a wholesome kind of exercise where uh, you are using Lagrange multiplier method in full force. Okay. So this is the general method of finding absolute extrema of a function. So if this is so in this case, this is not a level surface, right? It's a domain. So you break it into inside and the boundary. Inside you use first derivative, second derivative test. You actually don't need to use second derivative test because you're finding absolute extrema. But if you were also asked to find local extrema, then you would use second derivative test. And then on the boundary, you get a constraint, right? You get a level surface, and there you use Lagrange multiplier method. So you'll see several of such problems in the tutorial. Okay, now finally, let us extend Lagrange multiplier method when you have two constraints. So the question is, find extrema values of f subject to two constraints, g equal to k and h equal to l. So there are two level surfaces and you want to find extreme values. In other words, find extreme values of f when the points lie on the curve, which is the curve of intersection of these two level surfaces. So if you have two level surfaces, they may not meet at all or they meet on a level curve, right? On a curve. It's not a level curve really, it's a curve. So this is the picture. This green surface is h equal to, it's written h equal to c, but h equal to l. and this orange surface is G equal to K. They meet on this curve C. Okay. What is the method? Method is you compute gradient of F, gradient of G and gradient of H. You find values of X, Y, Z, lambda and mu which satisfy gradient of F equal to lambda gradient of G plus mu gradient of F, G equal to K and H equal to L, and then you compare the values like this. Now why is this working out? Let me explain this to you pictorially. So you remember what we got last time when we had only one constraint. So in this particular case, what happens is when you look at this surface G, gradient of G is perpendicular to this curve at this point, and similarly gradient of H is perpendicular to this curve at this point, right? And gradient of F is also perpendicular to this curve. So we have three vectors which are all perpendicular to a curve. Therefore, they should lie on a plane, right? In R3, if you have a vector, a fixed vector, and you get three vectors which are all perpendicular to it, then they should be lying on the plane whose normal is this fixed vector, right? Which is the direction of the tangent line to C at this point. So therefore, this is what you get. I'll explain this more in the live session, but I have deliberately skipped the proof because I want you to think about what's going on. Okay, it's a very straightforward extension of what we have done for the other two cases. When we had two variables, one constraint, and three variables, one constraint. So let us stop here.